it has 11 problems on it, which is why I've got it as 11 problems. You'll get a simple reflection problem. You're going to get a simple mirror problem. You'll have a diverging lens, converging lens. So those will be out there. You'll have a paperweight problem or some object where you're looking at the different indexes of refraction. We'll talk about the lens maker's equations and contact lenses and that kind of stuff. We'll get to those here. And then you'll have at least one 2-lens problem. So they're going to be, and they'll have a convex and a concave mirror problem. So you'll get a variety of different problems, but there's only 11 of them, and it's only over optics. So that's the final, and it's 8 a.m. on May 9th. And I don't know about the baseball guys, because that's usually when they hit district tournaments and stuff. So holler at me if we have to set up an alternative time. We haven't usually had to do that, but and Beverly will be over here for you guys, and then I'll be over there for Tonkawa. So, but we're rapidly approaching the end. So some of the reasons why I get surprised from the medical side and from some of the medical programs why we don't do a whole lot more with Physics 2 is because we get things like this. So what we're going to do is we're going to find the energy of a photon with a frequency of 6.3 times 10 to the 16 hertz. And then we're going to do one with a wavelength of 528 nanometers. So while this is just a straightforward calculate the energy problem, now with laser surgery, laser ablation of skin deformities, laser ablation of tattoo removal, laser ablation of tumors, the energy of the wavelengths of the light that you're using, or any of the electromagnetic waves, whether you're doing ultrasonic, or you're doing UV, or you're doing gamma rays, or you're doing whatever, it becomes real important, because the nice thing about the lasers is you can pinpoint exactly where that laser is going to go, and you want that energy placed right where you want it to be. And you need to know the magnitude of the energy. So from Planck's equation, and you'll see it as the energy is equal to Planck's constant times the frequency. In chemistry, you usually see frequency given by the Greek letter nu, but it's still the same. It's still the same equation that we've got. So my energy is going to be Planck's constant times that, and my energy is my Planck's constant is 6.63 times 10 to the minus 34 joule seconds. Now remember, frequency has units of 1 over seconds, which is a hertz. So when I do this multiplication, my units are going to end up in joules, because I'm going to divide out the seconds. So it becomes real important just how much energy am I putting into my system, or how much energy is going to be absorbed. So if I've got a frequency, it's a pretty straightforward calculation. It's going to be 6.63 times 10 to the minus, I didn't write the 34, I said it, but I didn't write it, 10 to the minus 34 joule seconds. And then I'm just going to multiply by the frequency, 6.3 times 10 to the 16, 1 over seconds, because hertz are 1 over seconds. And then I plug that into the calculator, and it's 4.18 times 10 to the minus 17 joules. So if you think about what happens in the laser, this is one photon. And then I get intensity, and we've talked about intensity. And so intensity is going to be a whole bunch of those photons applied to the joules, and so you can put in a whole lot of energy. And it really doesn't take much. I mean, it really doesn't take much and as we know that, I mean, because think about ultraviolet light and sunburns. It really doesn't take a whole lot. So if I want to do the next one where I'm given the wavelength, remember that my speed of light is equal to the frequency times the wavelength. So to find frequency, I'm just going to take the speed of light divided by the wavelength. So that's going to be like 3 times 10 to the 8 meters per second divided by the wavelength, which is 528 times 10 to the minus 9 meters, because that's nanometers. And for those of you who want to know what 528 is, 643 is the helium neon that you guys have been using in lab. 528 is actually an argon laser. It's kind of a bluish green color when you actually see it. And that's going to have a frequency of 5.7 times 10 to the 14 hertz. And so now I'll just do the same calculation. E is equal to my 6.63 times 10 to the minus 34 joules seconds, 5.7 times 10 to the 14 hertz. And that's going to end up giving me 3.78 times 10 to the minus 19 joules. So while the calculation is pretty simple, the understanding of what you need that calculation for becomes kind of important. Okay, so let's talk about Snell's law. We talked about Snell's law, we kind of showed it. One of the things about Snell's law, and I'm going to start with what happens with Snell's law. Snell's law is actually the index of refraction times the angle of sine of the angle of incidence is going to equal the index of reflection, or the refraction of this item that it's going in, times the angle of reflection. So that's Snell's law. Now, even though I put it on the slides, I kind of quickly went over it. Where this is coming from is that if I look at my system, and I've got my normal force here, and let's go ahead and say this is glass, and this is air. So N for air, we said was approximately 1, and it's very, very close to 1. And glass has a whole range. In fact, if you go look, this happens to be a table off the internet. And let me scroll in so we can see it here. Let's see if we can get it to focus. So this just happens to be, I've expanded it out. And so here's a whole bunch of glass. This is something that's called crown glass. This is flint glass. And these are pure type glasses. And this is a Pyrex, which is a borosilicate glass. There's sapphire for you. There's sugar solution. See, I'll scroll down here. There's sugar solutions. So we get a lot of index of refraction, and glass has a whole host of them. It depends on what kind of glass that you have. Leaded glass is going to be a little different. They're all going to be a little different depending upon what kind of glass you have. And then you've got ranges of indexes of refraction. Now, when you guys are doing your homework in WebAssign, use the table in the book, because flint glass has an index of refraction between 1.6 and 1.62. You want to use the value that they give you in the text, because if you use one of these values, you may not be close enough to the answer in WebAssign, and WebAssign gives you the even though you've done the problem absolutely correct. So you can't just necessarily go look up an index of refraction on the internet because of that. So you do want to be very, very careful about that when you're doing it. Even though you're doing it correctly, it's just that which index of refraction did WebAssign plug in for its answer. And I'll tell you what table it is, and I think when you do the problems in WebAssign, you can click for the references and the table will pop up for you, so that you'll be able to do that. But basically what's happening here is when I come in and I have my incident ray, and so glass is about, we saw that was approximately, let's say it's approximately 1.6. So this is when N2 is greater than N1. We said that this is going to bend inward. And what's happening to us in this situation is I get a little bit of a change of the speed of light associated with the medium in which I'm in. So while we use the speed of light as being 3 times 10 to the 8 in a vacuum, we do get a slight change. And your book actually really goes through those different pictures of what's happening, but the thing is you will get that change in the speed. And where Snell started with is when you looked at this, we said with this angle of reflection, refraction, comes in, and this is the angle, the incident angle, that we find that these two angles are going to be related to the speeds that a light is having, and that comes into a constant. So that's just another version of Snell's law. So when we're going to get this, and we're going to do a problem that utilizes this form of it versus utilizing this form, but that's the form that we use most often. Okay, that's the form that we use most often. So we're going to start with that. So what we want to do is we want to find the angle of refraction for light entering fused quartz from air with an incident angle equaling 30 degrees. So basically we've got that situation. We can put in, our angle comes in, our light is going to be here, it's 30 degrees. This is air. So we're going to have an index of refraction of 1. And if you look at the table in the book, and we know that this is fused quartz, this index of refraction is 1.34. The indexes of refraction are ratios, so they don't have any units. And this is the angle that we're trying to find. So that's the angle that we're trying to find. So it's just going to be a Snell's law problem. N1 sine of the angle 1 is equal to N2 sine of the angle 2. Since I know N1, I know N2, and I know the sine of the angle, I get N1 divided by N2 sine of the angle. So I get 1 divided by 1.34 times the sine of 30 degrees is going to give me a value, and that value ends up being 0.349. So the angle is going to be the arc sine of my 0.349, and that's going to end up being 20.4 degrees. And we kind of showed on the presentation that if I'm in a situation like this, where this is air and this is something else, but when N2 is greater than N1, this is going to bend towards the normal. So this is going to bend that way. Now if I go the other way, where this N2, it says air, or is still the greater one, we'll say it's 1.33, we'll go ahead and use water. If I have my ray coming up from here, this is going to bend away from the normal if this is air. So if I'm going this direction, where my beam is, so that this is coming in, I'm going to bend away from the normal. So you can play with those in order to have that work out. So let's do a problem real quick on that one, because one of the things that I didn't cover and it's in that chapter, is something called the total internal reflection. And this is what gives us fiber optics. Because what's going to happen when I have total internal reflection for fiber optics is I'm going to end up with a beam of light that gets totally reflected back inside the fiber and back inside, and that's what carries the light through the fiber. So I use total internal reflection for fiber optics. If you're a swimmer and you've been in the swimming pool, you've experienced total internal reflection, because you know that there are times that you look up to the surface of the pool and the surface of the pool looks mirrored and you don't see anything above the water. And that happens when I get total internal reflection. So what happens is, I'm coming in, this is water, so this is like 1.33, this is air, so this is like 1. There's a point at which this angle, when I do it, it's just going to go right along the surface, and it's not going to refract out. And anything greater than that, so anything that I move up over here, it's going to be totally reflected. So I'm looking for this point where this happens, where it comes right along that surface, and we call that the critical angle. So that's going to be the critical angle for our situation, and we can find that. And this happens when we're going to say, this is N1, and this is N2, because we use N1 and that's the medium, the from medium to the to medium. And when we do that, the sine of the critical angle is going to equal N2 divided by N1, where this is our N2 and this is our N1. And that's going to be the angle at which we get the total internal reflection. So if I'm doing water, that's going to be the sine of the critical angle. And that's going to be my 1 divided by 1.33. Do the critical angle is going to be the arc sine. And that gives me 48.6 degrees. So for water, so if I'm in the swimming pool and I'm the little diver out here and I've got my little glasses and I'm looking up here, this is when I'm looking up and it looks like the surface is a mirror. And a lot of us at least have had that experience. So here's a problem that gives you the how all optics is really, really huge. Because a lot of your equipment, like your x-ray machines, your MRI machines, your sonographs, all of those are going to rely on some of these principles of optics. So what we're going to do is we're given a situation where this is liver tissue, and this is a tumor tissue. We're going to shine in a beam to the surface of our tissue, and we're going to know that this angle is 50 degrees. It's going to go in to the tissue. It's going to refract. It's going to bounce off the tumor. And then we're going to get the refraction back out. And we can measure where it comes back out. We can locate that point. And we're told that this is 12 centimeters away if I go at that angle. And what we want to do is we want to find the depth at which the tumor is present. So we want to locate where that tumor is. So what we're looking for then is we're looking for this. We're looking for D. And it turns out that our detector, we know the speed at which this beam goes in, and we can pick up and we can use a detector and find the speed at which this goes out. And we find out that that's 0.9 of the speed that went in. Okay? So, and this is something that's totally doable. We actually do it. We can measure the intensity of, we know the intensity of what we're sending in, we can measure the intensity of what comes out, so we can relate it back to the speed. We can measure where it comes back out, so we know we can figure out what this is. So, we're going to use this version of Snell's law. That the sine is equal to, the ratio of the sines are going to be ratios of our speeds. We're going to utilize that, but we already know that that speed is 0.9 of this one. So there we go, the one going in, those will cancel. So we know that the ratio of the two angles here is equal to 0.9. We know, because we measured, we know exactly how we set up the system, so we know that the sine of the angle is going to now be 0.9 times the sine of my 50 degrees. And I can figure that value out. And this is going to give me the angle, when I actually calculate it, I didn't get, this is 43.6 degrees. So what that means is that this angle right here is the 43.6 degrees. Now, because of how this is set up, that angle is that angle. And we can use the symmetry of this situation to tell us that that's 6 centimeters. Because it's halfway. Because we know that this angle has to equal that angle. And so that gives me a right triangle. So now I can do that. I can look at it as the tangent of my angle. This angle here is the opposite over the adjacent. And that's our 6 centimeters divided by the depth that the tumor is sitting at. Let me scroll out so you can see the whole picture and everything. So now I can calculate D is equal to 6 centimeters divided by the tangent of my 43.6 degrees. Gives me a depth of 6.3 centimeters. So by understanding the equipment, and if you think about this, this is also kind of like a rangefinder for fish, okay? Except this time we're using light waves instead of sound waves. We're using an electromagnetic wave instead of a sound wave in order to get there. And we know that this material is different than this material. So it's going to have a different index of refraction or reflection or refraction for that material. And what's really interesting, if you think about it, my brother about 4 years ago was diagnosed with a brain tumor. And what's really interesting about the brain tumors is that his brain tumor was about the size of a grape. And it was within all the brain matter. And under normal kinds of X-rays or normal kinds of things, you can't. And actually, if you were to do the dissection, you could not tell from the dissection this from the brain tissue. But on the MRI, because of the reflections of the different wavelengths, this glowed like crazy. So on the images that they had, they could actually pick up all the different tendrils and all the different things that they could see out there with respect to the tumor. But when they did a cross section, or you actually looked at it in terms of the tissue, you couldn't really see the difference. And by looking at how that reacted with the different wavelengths, it made a huge difference. So we can utilize a lot of different medical imaging, and a lot of your big hospitals will have an imaging physicist that's looking at exactly how these wavelengths are interacting with the different materials in order to pick up tumors, in order to pick up cysts. That's how they can tell something's the difference between a cyst and a tumor. That's how they can tell a lot of different things associated with materials by looking at their various indexes of refraction, looking at how they respond to various wavelengths and energies of the light. So there's a lot of cool stuff there. Lots of cool stuff. All right. So now let's look at some image problems with a mirror. Okay? So what we're going to do, and unfortunately today I forgot a protractor, but you can do this as a protractor. We'll at least go through the exercise. I have my sketches drawn. So what we're going to do is we're going to calculate. Let me do a different pen, because that pen is always drying up. Let's see if this is going to do all right today. All right, we're going to calculate. Let's see. I'll have to scroll in. Okay, we're going to calculate the properties of an object in front of a concave mirror of radius 5.08 centimeters, and the object is going to have a height of 1.27 centimeters. So that's what we're going to do. I'm going to reach in, and I should have my ruler. I do have my ruler. And for those of you who are really bright and remember, there's 2.54 centimeters per inch. When I worked the problem out yesterday, I was using an inch ruler, which is why the numbers are the way they are. And the paper that I had, my graph paper, was actually marked out in inches, which is why I did it the way I did it. But so this is a half a centimeter or a half an inch, and that's that's 2 inches. So you can actually do these things to scale. So I'm going to draw my principal axis. Okay, I'm going to draw my principal axis. This is where I'm going to put my mirror. This is the radius of curvature, that's the radius of curvature. And on my first object, I'm going to put at 6.35 centimeters. And if I do that, that's going to be right about here. And then I've got it to be about a half an inch, because that's what I said I was doing. So I'm going to put my little object in here. So I can actually, and you can do these to scale, so I actually have my system here. So this is R. This is where the mirror crosses the principal axis. And we also showed on Wednesday that 2R is also equal to 1 over the focus. So if I do my 2R, it's going to be 2 divided by 5.08 centimeters. And my focus, when I do that, if you want to play that game, 2 divided by 5.08. Oh, clear. Should be 2.54, which means I can actually mark my focus in here. So this is where the focus of my mirror is. I'm bummed I didn't bring my my protractor, because it would be helpful to have the protractor, but it'll work out. So what we do is when we draw the ray diagram, the first thing that we're going to do is we're going to take the top of our image to the principal axis. This angle has to equal that angle, so I'm going to approximate it, so this may not come out perfect because I don't have my protractor. But that angle equals that angle, and so what we do is we play the bounce game. If you use your compass, and you get your nice compass and you get your concave mirror that's out there, the next thing you do is you take the radius of curvature, or through the radius of curvature through the system, and you draw your line, because this is going to reflect backwards, so that'll be there. So my image should appear somewhere in here, and it's going to be upside down, and it's going to have that top to it. So if we want to do this mathematically, we use the mirror equation, which is 1 over p, and p is this distance here, plus 1 over q is equal to 2r, or r, 2 divided by r, or it's equal to 1 over the focus. I chose to keep it that way when I calculated it out, and I get 1 over q is equal to 2 over r minus 1 over p. And when you do this, you get 2 over 5.08, and you can leave everything in centimeters, 6.35 centimeters. So that gives me 1 over q is equal to 0.236. Q then becomes 4.23 centimeters. I can then calculate the magnification. The magnification is minus q over p, minus 4.23 divided by 6.35 gives me a minus 0.666. The minus sign says it's inverted, which is exactly what we got up there on our image. We got it that it was inverted. And then I can actually calculate what that would be. That's 1.27 centimeters, which is what the original image height is. And it's going to be 0.666 of that. It's going to tell me it's 0.846 centimeters. So it's something that's smaller, and that's exactly what our image said. It's something that's smaller. And if you do this with nice precision, you can actually measure it and show that, yep, that really is. So we said if this is really 1.27, and that's about that. And I go over here, and that says it's about 0.8. So you can actually use the geometry to verify your calculations. Now this, I actually purposely set this up so where I've got my image on the outside of the radius of curvature. We're now going to do it where P is going to be 3.81 centimeters. I follow the same practice of how I draw my diagrams. I follow the same practice. And if I can do a calculation, I know that 1 over q is equal to 2 over r minus 1 over p. Plug in my numbers, I get 2 divided by 5.08 minus 381. Q becomes 7.62. My magnification is equal to minus 7.62 divided by my 3.81. It gives me minus 2. Still it's going to tell me that I'm inverted. But now I'm going to be twice the height of my object. So the magnification is going to be, I'm going to get minus 2 times 1.27. It's going to give me a minus 2.54 centimeters. So I'm going to be over here, and it's going to be bigger, and it's going to be located at 7.62 0.62 centimeters away. So it's going to come out back. Now let's do one where it's inside the focal point. Okay, it's going to be inside the focal point. So P is now 1.27 centimeters. Still do the same calculations. I get Q, I get 2 divided by 5.08 minus 1.27. I sat and drew the picture, but I didn't actually do the calculation, so let's do it. 2 divided by 5.008 minus 1.27 inverse. Do the inverse. Gives me a negative 2.54 centimeters for Q when I actually plug it into the calculator. Now the negative sign says the image is going to show up on this side of the mirror. And this means this is going to be a virtual image, where the other two images that I actually just showed, or we actually just calculated, are real images, because I can put a screen there and I can actually see them. Those are real images. So if I look at it, and I went ahead and printed out the picture in the book, so I had a nice pretty picture. Nice pretty picture. This is the case that we're doing. So this was the first case that we did. And here's the third beam that you can do. I take my beam that hits the mirror, and then if you look at this, you've got your normal there. This angle has to equal that angle, and that goes through the focal point, so that you have the focal point. You can go through the focal point there and come out parallel. That's one way to do it. Or you can do it the way that we just did it. Okay, you can do it that way too. So there's a couple ways to do these geometrically that allow you to really check your answers. But this is when the object is outside of those pieces, and now my object is inside the focal length, and now I have to worry about how I do this. I still can go through the focus and get my ray there. I can still go through the focus to go there. I can do all of those, still draw the same ray diagrams, but my image is now at the back. And now my image is also upright, because when I do the magnification is minus, and I do my minus Q. And we said that that was a minus 2.54 divided by my P, which in this case, when we did it at this one, 1.27. Yeah, 1.27. So if I plug that in the calculator, I get this. The magnification is 2. My magnification is 2, but it's virtual, and because it's positive, it's upright. And when you do a diverging mirror, which is what I will do on Monday, and then we will progress on. We'll do some other problems on Monday and do some more. We'll start talking about in paperweights and looking at those paperweight problems and things like that. But I could do the same ray diagrams, but now I have my focus on this side of the mirror, my radius of curvature on that side of the mirror, and I still do the ray diagrams the exact same way. I don't change up how I do those ray diagrams. Okay, so Monday we will progress on with doing paperweights and doing objects inside of different mediums. We'll play with a little bit more with mirrors, and then we start lenses towards the end of the week. And we're down to like 6 classes left, guys. And I have your test. I have your test.